And the next talk is by Yochai, Blau and Michaeli from the Technion, the Perception-Distortion Tradeoff. The talk will be given by Yochai.
Okay, my name is Yochai. I will present the Perception-Distortion Tradeoff, and this is joint work with my advisor, Professor Michaeli from the Technion. So in this work, we will discuss image restoration, where you have some low-quality image, and you want to obtain a high-quality version of that image. And very common scenarios can be super resolution, where you try to enhance the resolution, in painting, where you try to fill in missing pixels, denoising, where you try to repress noise, and so on. And in these image restoration tasks, we first ask what are the goals of the image restoration process. Now, the first goal is that you want your reconstruction to be as similar as possible to the ground truth original image, which we will call low distortion. And second, you also want your reconstruction to have good perceptual quality, which means not have any artifacts, blur, noise, or anything that would disclose that the reconstruction is not the original ground truth image. Now, it may seem that these two goals are the same, but they are not. For example, I could obtain perfect perceptual quality by disregarding the input and just drawing some natural image from a database, which would of course be very bad in terms of distortion. And intuitively, it may seem that if you have low distortion, you should get good perceptual quality. For example, if you can perfectly reconstruct, then you have zero distortion, perfect perceptual quality. But what we ask is, what about the scenarios where you cannot perfectly reconstruct, such as super resolution, denoising, dehazing, in painting, deblurring, etc. And in our work, what we show is that in these scenarios, you cannot obtain both low distortion and high perceptual quality. There is a trade-off between these two, and one will come at the expense of the other. Now, there has been empirical evidence of this. For example, we can look at the SR gun paper from CVPR 17, and what these authors show is a super resolution algorithm which is superior in perceptual quality as rated by human observers. But when we compare this model to other models which excel at distortion, it's apparent that the SR gun is far worse in terms of distortion. On average, this is 2.5 dB in PSNR. And this is not the only algorithm showing this phenomenon. So let's do the following experiment. We'll take super resolution algorithms and we'll rate them by two measures. The first will be a popular distortion measure. Here it's the squared error. And the second one will be a quality measure which does not rely on the ground truth image. So it only sees the reconstructed image and predicts its perceptual quality. And here we'll use NIQE, which accurately predicts human opinion scores. So in this two-dimensional plot, where you would want your algorithm to be is here, where distortion is low and perceptual quality is good. So what we did is we took 15 super resolution algorithms, all from recent years, and we measured them according to these two quality measures, and this is what we got. And the first thing you should notice is that no algorithm is close to the origin, which means that no algorithm is good both in terms of distortion and perceptual quality. And we can even look at an example, so let's take this input. And let's start from the upper left corner where distortion is low. And what we see is that the reconstructions are blurry and unnatural. And as we gradually move downwards, they become more and more realistic, but at the cost of higher distortion. And here the reason is that the features making these realistic are hallucinated and never appeared in the ground truth image. Now we can ask, why is this happening? And most prior works attribute this phenomenon to the mean squared error being a bad metric for measuring similarity between images. And indeed, over the past decades, there have been many other suggestions for more advanced similarity, more perceptual, more semantic similarity metrics between images. So if we replace the squared error with a more advanced similarity measure between images, will this problem be solved? And the answer is no. Here you see the exact same plot for the advanced measures, SSIM, multiscale SSIM, IFC, VIF, and the distance in the deep feature space, here specifically the VGGNet. And as you can notice, in all of them, the origin is blank. So no algorithm succeeds in being good at perceptual quality and distortion, and this is no matter how you would choose to measure distortion. And we even tried this in a larger scale. So together with Roy Mehrez and Professor Lee Zelnick-Manor from the Technion, we proposed a challenge at the last ECCV. And to make things short, what we asked people to do is, in this two-dimensional plane, improve as far as they can in perceptual quality. That is, move as downwards as possible. And 95 submissions later, this is what we got. And again, let's look at the origin. No one succeeded in improving in perceptual quality while keeping a low distortion. This was only possible by degrading the distortion, and indeed they succeeded in obtaining better perceptual quality. Now, what we do in our work is mathematically prove that such a trade-off exists. So think of a two-dimensional plane where the first axis is distortion and the second axis is perceptual quality. And again, if you would want your algorithm to be at the origin where distortion is low and perceptual quality is high. However, this is impossible. And the reason this is impossible is there is a bound in this plane, and all algorithms must lie above the bound. Now, if you have an algorithm here in the red dot, if you want to improve in distortion, that is, move to the left, you must move upwards and degrade in perceptual quality. And if you want to improve in perceptual quality, that is, move down, you must also move to the right and degrade in distortion. So, to prove such a bound exists, we have to mathematically define what we mean by distortion and what we mean by perceptual quality. So in the image restoration scenario, you have some underlying natural image X, but you only have access to a degraded version Y. And what you want to do is, with your algorithm, reconstruct X hat, which is the reconstructed image. Now, in statistical terms, you can't think of X as being drawn from the distribution of natural images, Px. The degradation being defined by some conditional distribution, and this is the most general way to define a degradation. It could account for additive noise, downsampling, blur, etc. And all we assume on the degradation is that it is non-invertible. And the algorithm can also be defined by some conditional distribution. Again, this is the most general way to define an algorithm. Now, let's start with distortion. How would you define distortion? Well, you need some dissimilarity metric delta here between images, and then what you do is take a mean over natural images, draws of natural images, and over the randomness of the degradation. And we have minor assumptions on this delta dissimilarity function, and that means our theory now applies to all popular similarity metrics between images, the squared error, SSIM, the VGGNet, the deep feature space, etc. So distortion is very straightforward, but what about perceptual quality? How would one define mathematically perceptual quality? Well, we start by following the common test, which is, as I show now, what people do to quantify perceptual quality is take either the natural or the reconstructed image, each with 50% probability, and then they ask human observers, is this image real or fake? Is it the natural or reconstructed image? And what they quantify is the success rate in this task. And if one cannot distinguish between these two, p-success is low, and this indicates good perceptual quality. Well, this is not a mathematical definition because there is a human in the loop here. But what this is a Bayesian hypothesis testing scenario between the hypothesis of natural and reconstructed image. And what we can easily show is that in this scenario, p-success is proportional to the total variation divergence between px and px hat, the distribution of natural images and the distribution of reconstructed images. And therefore, following this common test, what we do is define mathematically perceptual quality as the divergence between Px and Px hat. And we only have minor assumptions on this divergence, and therefore our theory will apply to all popular divergences, total variation, Kullback-Leibler, Wasserstein, etc. So let's recap this first part. We study the trade-off between distortion and perceptual quality. Distortion is defined by a mean over some dissimilarity metric. Perceptual quality is defined by the divergence between Px and Px hat, the distribution of original and reconstructed images. So the first thing is that intuitively, it may seem that if you minimize distortion that is moved to the left, you should obtain good perceptual quality and a small divergence between Px and Px hat. But the truth is that this is not what happens, and we can show this even on very, very simple examples. So let's take this simple example. We have an image. It has 100 blocks. Each block is either an MNIST digit or a blank space. And now we add Gaussian noise, and we're trying to reconstruct, that is, the noise. And we do this only by minimizing distortion. And we'll start with the most popular distortion, the squared error. And we can do this in this example analytically. So there's no approximation here. We use the MMSE estimator, and these are the reconstructions. And when the noise level rises, you can see the reconstructions become blurry and do not follow the statistics of the original image. And you may say, okay, the squared error is only one distortion function, and it's known to perform averaging, and it's a very known shortcoming that it causes blur. What about other distortion functions, which may be better? What about those that are confined to choose from the original signals, the original possible signals? So one such distortion is the 0-1 distortion, which we can, again, without no approximation, analytically minimize by the map estimator, and this is what we obtain. So even with the map estimator, which is very common in image processing, you can see that when the noise level rises, the images become more and more dominated by blank patches, and they certainly do not follow the statistics of the original images. So minimizing distortion does not lead to good perceptual quality, but these are only two distortion functions. We can ask a more general question. Does there exist some distortion measure that will lead to good perceptual quality? And we will actually answer a similar question. Does there exist a stable perceptual distortion measure? And by stable, we mean that it will not work only for some specifically tailored scenario. And the answer to the existence of such a stable perceptual distortion measure is there does not exist one. And we show this by the following theorem. Let's say you have found some magical dissimilarity metric delta, and you minimize it, and by minimizing it, you obtain perfect perceptual quality. What we show is that there will always exist an infinitesimal perturbation of the problem, such that if you minimize the same distortion function, you will not obtain perfect perceptual quality. So you might be able to tailor it to some very specific problem, figuratively speaking. Maybe you can find some magical distortion function for denoising with Gaussian noise of sigma 20, but it would not work for sigma 21. So clearly minimizing distortion is not always the right thing to do depending on what your objective is. But now we don't want to only talk about the leftmost point on this bound. We want to talk about how this trade-off, how we can characterize this trade-off. So we want to ask for any distortion level, what is the best perceptual quality you can obtain? Which is asking how far downwards can you move in this two-dimensional plane. And this corresponds to the following problem. What is the optimal perceptual quality subject to some level of distortion? And we want to ask this for any level of distortion. Now, there is no closed-form solution to this problem in general, but we can prove some characteristics of this function, the perception-distortion function, which is the bound plotted here in blue. So namely, the perception-distortion function, the bound here in blue, is always monotonically non-increasing and convex, and this is true for any distortion measure delta and for all popular divergences between Px and Px hat. And please note that what convexity implies here is that in the low distortion and high perceptual quality regime, the trade-off becomes stronger. Another interesting question is the following. Let's say you have the algorithm which minimizes distortion. And now you want to obtain an algorithm which has perfect perceptual quality. How much would you have to pay in terms of distortion to perform this shift? And what we can show for the RMSE distortion is that you would never need more than a factor of square root of 2, which in PSNR is 3 dB. So rephrasing simply, you never need to degrade more than 3 dB in PSNR to obtain perfect perceptual quality. Now, let's go back and look at the super resolution algorithms. And let's take the one with the minimal distortion. This is EDSR. And now let's move a factor of square root of 2 to the right, which brings us here. And what you see is that to date, algorithms with the best perceptual quality are actually compromising about 3 dB in PSNR, which aligns with the theory we have just discussed. So we have shown the perception-distortion trade-off, and we have discussed its theoretical characteristics. But the next question could be, is there an algorithmic way to approach the perception-distortion bound? And the answer is yes, there is. And in fact, this has been done prior to our work by gun-based image restoration schemes. So what these works do is define a loss function. What it has is a distortion term and an adversarial term of guns. And this is actually approximating the theoretical distortion and the divergence between Px and Px hat. Now, if you think of lambda as a Lagrange multiplier, minimizing this loss for some value of lambda is solving the perception distortion function for some value of d. And therefore, if we minimize this loss for a set of lambdas, we are actually traversing the perception distortion trade-off. So we do this. We take MNIST digits, we add noise, and now we're trying to reconstruct not by minimizing distortion, but by minimizing this loss for different values of lambda. And what you see here, each dot is a neural net optimized for a different value of lambda. And what you can see is that when we allow for higher distortion levels, we indeed obtain a smaller divergence between Px and Px hat, and this does correspond to a gradual increase in the perceptual quality of the reconstructions. So let's talk about the take-home messages. There is a trade-off between perceptual quality and distortion. And what this implies is that there is no optimal algorithm because this is task-dependent. So if you're trying to reconstruct medical images, you would perhaps want algorithm A, which is low in distortion and does not hallucinate things which weren't there. But if you're trying to enhance your personal photos, perhaps algorithm B is better, which would make them look quite nice. So what you actually want to do is define the distortion level that your task can tolerate. And once you have done this, you would like to move as downwards as possible to get as close to the perception distortion bound as you can. And there is actually a systematic way of doing this, and this is by using gun-based image restoration schemes. Thank you very much, and happy to take questions.
Of the output of algorithms that would apply to your, to the bound of your curve, of your optimality curve.
So if I understood correctly, you're asking when you change the image, how would that change the dot on the curve?
An axis. I'm missing an axis of how a little bit changing the image would influence the result of an algorithm.
Okay, so our current analysis does not address single images, but an algorithm in whole, which in theory should apply to all the distribution of natural images. So each dot here is not for a specific image, but for an algorithm which looks at the whole distribution. We, in this work, have not analyzed this trade-off for a single image, and this could be further work.
Any more questions?
Hi. So I was wondering if you can relate to variational autoencoders that, if I remember correctly, they actually minimize the distortion loss, and there is kind of an open question, why do variational autoencoders are blurry and GANs are better perceptually?
So again, you're talking about a specific algorithm. It will also apply to any algorithm. Variational autoencoders also, you can try to perform image restoration with them, and there will be some form of loss on the distribution with variational autoencoders and on the distortion. And again, the trade-off will apply to variational autoencoders. There's nothing special about them that can help them break this bound. So GANs do it differently. They use specifically the MSE and the divergence on PX and PX hat, and these do it quite differently, but the same trade-off applies.
Let's thank the speaker again.